Greetings, salutations, and welcome back to another video. Now, hopefully in this video I shall cover some of the electronics, but first of all, I have me a pot of black paint and a paintbrush, so I figure I'm going to try and cover as much of this in black as possible, and then go from there. So with that painted black, I'm going to be adding lines here as a grid, either in green paint or white, just to highlight at its nodes where the clamping holes are. It's not very clear at the moment. I mean, it became more clear as the paint dried. You can see them clearly now. But yeah, that'll just help make it easier for me to find them when I need them. But onto the power supply. We have the power running in here through the socket. It then comes to the switch, and from the switch into the power supply unit, and then into the CNC shield. That's what we've got right now. What I want to do now is just quickly set up the system that will run the spindle, and that's in both directions at variable speed. And that's a system completely of me and my father's design. Yeah, it's quite experimental compared to some of the purchasable systems out there. But I'll give you a run through. It works in theory, we just need to see if it works in practice. So, how are we going to control this motor? Well, we've got the circuit drawn out here. Excuse the way it's been drawn, it's not very neat, and there are more compact and precise ways of drawing it, but that's what I've got. Here we've got the 24 volt power supply with its positive and negative channels. Now the positive comes down into this relay here, and basically on its neutral position, the power routes through this way, through the motor in that direction, which makes it spin one way, and when it's been switched to the other pole, it routes through in the opposite direction. So it's a double pole, double throw relay, which means that those are switched at the same time by the electromagnet. Now the electromagnet unfortunately has to run at 12 volts while everything else can handle up to 24 or 30 volts. So what we've basically done is thrown in a 100 ohm 2 watt resistor from the positive channel to dissipate a lot of power and to actually control the switching of that from a binary signal on the CNC shield, which means that it's either on or it's off. We are using an IGBT. Now an IGBT is an insulated gate bipolar transistor, and it's much like the TIP120s that are very commonly used for this kind of switching, like on the ramps board, except that I don't know why we don't use them more, because they are designed for over 430 volts and more than 20 amps of current through it natively, which is amazing given how small they are. But they're often used in things like car starter engines and ignitions and that kind of thing. They like to run on the negative side, so that's why it's after the relay on the power scale. But that just feeds back to ground. Now to control the speed, now that we've got the directionality, we're also on the negative side of the motor, because however these switch, the motor's negative will always come up through this channel. So we're taking it to another IGBT, which we are switching via PWM. So that means that it's on and it's off for short bursts, and that basically just, it sort of pseudo changes the speed. It's a bit more complex than that. But we've got a smoothing system here, but what that means is that as that increases, this system here will smooth it out and increase it more analogly than digitally, because PWM is just a digital equivalent of an analog signal, and then basically, yeah, control the amount of current flow going through the motor, and that will control the speed. So the motor changes direction through the relay, which just switches which way through the motor the power is going, and then the amount of current being drawn is controlled by the IGBT here, which changes its velocity. In practice, this is all we need. We have here our 1 kilo ohm, camera's way above me right now actually because I need to get this all in view, so we've got the 1 kilo ohm resistor and a little diode in there for that section. These are the IGBTs that I have. They are absolutely tiny, keeping in mind that these connectors, as you can see, to have a certain amount of current through it, a wire has to be a certain thickness, and so these are rated for 15 amps. They can probably take over 20, to be honest. It's just a safety rag thing. So yeah, that shows you what kind of thickness of wire we're talking about to carry these currents. And apparently this IGBT can take the same through those tiny little legs. Now I trust that because I bought them from a reputed source, but just to be on the safe side, I'm going to make a small heatsink to clamp these onto to try and dissipate as much heat as possible. I'm going to blow a little fan over the entire thing to keep it cold as well. Here's our relay with the two contacts for our electromagnet. Through the middle here we have the power supply, and then these will be giving the power out for the spindle. Now, it's a bit hard to imagine for some people, but basically what we want to do is we want to cross that with that, and that with that, and then take power from each of those loops to the motor. And that basically means that whichever way it flicks, the direction of current flow will be inverted. And that's just a small, well, it's not small, that's the 100 ohm 2 watt resistor going in from our power level down into there. So we're back up here with Axis, and as you can see I've made a start with finishing off the white lines. However, I ran out of my white paint and had to borrow my brother's, which is supposedly the exact same shade, but as you can tell, mine is a cold white while his is a warm white, and that aside, I'm almost out of his stuff as well, so I've had to order up some more paint to finish off that. But anyway, this is what we have. This is the real life version of my circuit diagram, and please excuse any sniffing and stuff because I've had a wonderful hay fever attack just now. But what's happening here is we've got the in and the out there. The out doesn't need a positive and negative because it changes, and we've just wired everything up like that. I've got two makeshift heat sinks on this side for the IGBTs, and those are coming out through here for our direction and speed wires that will plug into this board here. Now, if I can get this to focus properly, yes, just here, you can see spin N and spin DR. That's spin enable and spin direction. And those two pins are basically what we're going to be connecting to. However, there is a slight issue in that this is a version 3.0 board. You can't see it inside there because it's dark, but yeah, this is a version 3.0 board. And unfortunately, these boards were not designed with that native to durable built in. So it's actually using the wrong pins here. So I basically have to swap out for two other pins on here. I can't remember which ones off the top of my head, but I'll show you which. But we basically just swap around a pair of pins, and one of the end stops ends up being on one of the spin enable pins, but that side, it's not a big deal. So I'm going to get that wired up quickly and give it a quick test, hopefully. So we're mostly set up. I've got Arduino up just so we can use the serial port to just easily send G-code. That's mainly wired up. I've got the power in and made sure it's the right way around. And the spindle has been taken from there to here, so that's all ready to go. Now, according to digitaldroid.co.za, the important info to note when upgrading to durable 0.9 includes variable spindles now enabled by default. Z-limit D12 and spindle enable D11 have switched. So yeah, those are two you need to switch as shown in the diagram here. Z and spindle are switching over. It won't work if that isn't done. So I'm filming this post-testing. The testing was a bit of a mess and it wasn't really worth recording in many ways. But what was basically happening was that we did manage to get it working. We got highs and lows through there, we got the right speed settings and all of that. It was working really nicely as a test, until we actually plugged this in again, plugged the spindle in again, at which point it failed. Now there was an undue amount of torque being placed on it, and we think that might be the main issue, because it rotates decently nicely now. But there's also a worry that some back current was created, and either of those factors has fried this second IGBT, the one that controls the speed. So what's currently happening is that while this is powered off and the speed of the spindle is set to 0, that is having 24 volts running through it, which is the maximum amount of current and voltage, sorry, which should only happen when it's running at full speed. So at 0 it's now running at full speed. At full speed it's still saying the same, and what's basically happened is that the collector and emitter on that IGBT have short-circuited or fried, and yeah, we've managed to blow it, basically. But I've got 5 of those things, so I'll swap in another one tomorrow, hopefully, and give it another quick test. The thing is that tomorrow I am actually going on a week-long holiday, so I won't be doing any of this for a week. That doesn't mean you won't be getting a video. In fact, by the time this video goes up, I will have been on holiday for a little while. I'm hoping to get something else up that I've done over my holiday, but we'll see how that goes. So yeah, that's an update for that. Hopefully we'll get that done before filming ends, but we'll see. In other news, to do with the runner here and the sprocket within that I mentioned having trouble with in the last video, I've done multiple tests, I've tried multiple sprockets, I've taken apart and reassembled this little section here so many times today that it's not even funny anymore. And the main conclusion I've come to is that while it's a lot better, the motion just isn't really as smooth and as refined as I would want. So what I've decided to do is, if I cannot finish refining it by the time I go on a holiday, so I've got only a few hours left actually, if I can't finish it by then after the holidays I shall replace it with a printed rack and pinion. So the actual rack, instead of being the chain, will be a printed one, and that can be printed as a helical gear, meaning that it'll have constant contact and everything will be much more controllable. Now to me that feels a bit like a cop-out, because I wanted to make this as much as much a test of these things and as much a sort of everyday man kind of build. Like, you don't need to have a 3D printer to make some of this and test it. And unfortunately that doesn't seem like it'll be the case, which is also a shame because I've spent a decent amount of money. It's a small amount, but it's still a decent amount on these chains. But those can go away for another project, and we'll see what happens with those later. But yeah, that might be what I have to do. It works, but it jumps every so often. Every time it goes over one of the little rings in here, every time it goes over one of these, it kind of strains a bit and then goes easy again, and then strains and goes easy. And it's that kind of motion that we really don't want, that sinusoidal interruption that we don't want in the system. We want it to run smoothly throughout. So yeah, we'll probably just try it with a printed rack and pinion and see what happens. Since filming the last clip, I've come to a few conclusions. The first is that this motor had the collet lock on, but no collet inside, so it's pushing against the system and was under a lot more torque than it usually would be. The second is that it is a 12 volt motor, and unlike what I've been led to believe, can't handle the 24 volts. Now thankfully, because this system varies the voltage in order to control the speed, I can just run it at 50% or so speed at the maximum, and that should be okay. But with that said, there are a few other things that should be attended to along the safety line, and that includes putting in Shakti diodes, which are basically like normal diodes, except they switch at a much lower voltage. And the idea is to put one going from the emitter to the collector on each of these, so that any back current will be taken very, very quickly across the diode instead of across the transistor, which basically saves them and stops them from burning out. So that's going to be implemented after the holidays, but I have to pack and head. So thank you very much for watching, and I hope you'll join me again next time, and have yourself a good week.